I'd now like to introduce you to our presenter for today's webinar, Peter Stepien. So Peter is the Principal Engineer at research service provider ResTech, which is a joint partnership between Ampcontrol and the University of Newcastle. Since joining the team in 2007, he's carried out numerous investigations of earth fault-limited power systems used in mining, including electric shock incidences and the impact of VSDs. Before joining the team at ResTech, Peter worked for the Electricity Commission of New South Wales and the Centre for Industrial Control Science at the University of Newcastle. Peter received his PhD degree from the University of Sydney, is registered as a CPEng, and is a Fellow of Engineers Australia. Dr. Stepien also holds the position of Conjoint Senior Lecturer at the University of Newcastle and teaches as a casual academic. So please welcome Peter.
Thank you very much, Emily, for that nice introduction. And thank you, everybody, for joining the webinar today. So today's webinar is going to be about modelling fault scenarios to minimise asset downtime. So this is going to be an interesting presentation that's going to give some motivation for why we want to actually do that. Basically go through the methodology on how we actually set up a system that we can actually model the fault scenarios, and I'll go through an example of how that's actually being done. And then at the end, I'll just draw some conclusions from the presentation today. Okay, so to start off with, let's have a look at the motivation for why we want to do modelling of fault scenarios in the system. So obviously, we want to minimise asset downtime, and why we might want to do that is that if our asset is not operating, then we've obviously got a loss of revenue. Okay, so for example, if we're talking about a coal plant, it means that we're not producing coal. And also that can have also an operational impact on the plant as well. So for example, if the plant is being used for ventilation or for dewatering a mine, it's important that the asset is actually up and running. So assets are normally down during scheduled maintenance, which is a planned event, but it's also down when a fault occurs in the system. And of course, a fault is something that's unplanned and it's something that's not desired. Okay. So if a fault does occur, we obviously want to locate the fault as quickly as possible. And generally the process that we go through is noting what the symptoms are when the fault occurred, like what was running, what tripped, what are the voltages and currents doing at the time of the tripping. And then we obviously want to then take that and map it to some possible fault locations where that might have actually caused the plant to stop working. Now, of course, if this is being done at the time when the fault occurs, it can take actually a long time. However, if we want to speed up the process of finding a fault, we can actually beforehand model the fault scenarios and basically from a given set of symptoms determine what the probable fault locations might be. And of course, if we do that beforehand, that means when the fault does occur, we're going to be able to find the fault more quickly, and hence we're going to minimise the downtime of the asset and get it back into production again. So I'm hoping that the motivation is quite clear, and the motivation is actually quite justified. So I'll just go through now the methodology of how we actually go about modelling fault scenarios and how we might actually use that then to locate a fault. So the main areas for the actual fault finding process are defining the modes of operation of the plant, considering where the fault locations might be and the types of faults, and also defining what sort of symptoms we are looking for when we are doing our fault finding process. And then I'll go through with an overview of how we would actually locate a fault, and just a summary just to sort of close off this particular section. So defining the mode of operation basically is saying what is the state of the equipment, okay? In other words, what's the state of circuit breakers and contactors? Are they open? Are they closed? Are they in the process of closing? Okay, or things like variable speed drives. Are they going through a pre-charge sequence, or are they running? And of course, this is actually quite good because knowing what the mode of operation is helps us locate or localize the fault. Generally, a section that's not energized doesn't reveal a fault. Okay, there's no power to that section. Even though a fault might be present, we don't necessarily see it. Okay, and also the reason why we want to consider states where things are actually changing, in other words, when a contactor or circuit breaker is being closed, is that a fault might be present in an unenergized section. Okay, however, at the process of energization, the fault is then revealed. Okay, so maybe the best thing to do is just consider a simple earth fault limited system. And this will be a very simple example, just to sort of make the points that I want to make. Of course, a real system is far more complicated, but this one will basically have a substation with an upstream circuit breaker and a DCB with a contactor. Okay, so if we were to consider this type of a system, okay, if I was to draw it out, it would look something like this. So once again, I haven't included the things that would normally be in here. I've just decided to just highlight a few things. So on the left-hand side, we have a substation with a transformer in it, and then we have an incoming supply which goes through a circuit breaker. And that circuit breaker, for this example, as we'll see later on, would be controlled by a fault that happens within the substation, and that would actually open up. So that substation is then connected to a DCB via a cable, and within the DCB there's a contactor which then provides supply to the output via a cable. And I haven't actually shown what the DCB supplies. Okay, so when thinking about the modes of operation of this particular system, there's two things that are switchable. One is the circuit breaker on the input, and the other is the contactor in the DCB. And just to make it easier, I've labelled them as being HV for a high voltage input, say 11 kV or 3.3 kV, and LV for the low voltage side of the transformer, which might be, say, at 1,000 volts. So the first mode of operation is both the circuit breaker and the contactor are off, and they're basically shown there in the off position. Now, generally, the off state isn't a particularly useful state to do debugging as such. If we want to monitor what the currents and voltages are doing, or if when a fault does occur, to see how they might change. Because if everything is off, nothing actually reveals itself, other than if we were to manually go in there and make some direct measurements using some test equipment. But I've still shown it there as basically being, this is the initial state of the system before anything gets powered up. I've noted two fault locations there, which I'll mention again later on. And I've also noted 2 points of measurement, one labelled sub and one labelled DCB, which will also come up later on when we're looking at the current and voltage waveforms. So if we were to energize this particular system, we would normally start by energizing or by turning on or closing the circuit breaker. So the first mode of operation would actually be closing of the HV contactor, HV circuit breaker. So here I've given this a particular label, so I've called it mode O2S, in other words, off to substation being energized. Okay, and we'll see how coming up with labels for things is actually quite important if we're trying to formalize this, because whilst this is a simple system, these things can become very complicated when we're looking at hundreds of scenarios that we want to try and evaluate. So, so you can imagine this particular mode of operation as we energize. If there was a fault, for example, in the substation before the open DCB contactor, that would actually reveal a fault, because it would basically be closing onto a fault. Okay, and this is why we want to consider the modes where things are turning on. Okay. Now, the next mode after this would be when the actual circuit breaker is closed, in the closed position, okay, and and the LV and the DCB contactor is still off. Okay, and in this particular mode, we would assume that initially, if you were closing and there was no faults, the substation would be energized, and there would be power available at the input to the DCB. So if a fault occurred at this point in time, then it would reveal itself, and because the DCB circuit breaker is open, we can assume that the fault is not within the DCB as such. Okay, and you can sort of see now how a mode of operation is starting to be useful, because it sort of allows us to localize where faults might actually be. And this one here I've called the mode sub SUB. Okay, I've also used square brackets because it can be sometimes confusing between a mode and a particular point of measurement, which I've also labeled sub and DCB. So the next mode would be when we're actually switching on the contactor in the DCB, which is I've labeled here S2D. So we see now on the right-hand side the circuit breaker labeled LV is now closing. Okay, so this, if there was a fault within the DCB or downstream in the cable, it would be revealed when that particular contactor is being closed. Okay, and of course the final one in the simple system is when both the circuit breaker and the contactor are closed, and basically we have power to the whole system. Okay, and of course if there was a fault occurring in the DCB, that would then be revealed. Now, of course, if a fault occurs anywhere in a part of the system where power is applied, the fault is revealed. And of course, we'll see then the sequence of devices tripping will then give us clues as to where the fault might be, and also what the currents and voltages are doing will also give us clues as to where the fault might be. Okay. So this simple system has got basically 4 modes of operation, and of course, if you have more things downstream, that would create more modes. And of course, certain modes don't make any sense. So, for example, you wouldn't have the DCB contactor closed whilst the HV circuit breaker is open. So the modes of operation do relate to practical operations. Where it becomes more well, not necessarily complex, but just more modes is when you have parallel paths, because you need to consider, for example, a DCB with, say, 5 outlets. You have to consider all different combinations of contactors being closed. So next thing is to do is consider possible fault locations and types. Okay, and of course we want to consider all possible fault locations, all probable fault locations, because basically if we don't actually model a particular fault, then we're not going to be able to find where that fault is looking at the information from our system. Okay, that's usually the case. I mean, you can still get some information, but ideally what we want to do is we want to model all particular fault scenarios that might actually occur. So in this particular simple example, we've just identified 2 fault locations in the simple example. Okay, and of course, as well as having the fault location, we need to think about different types of faults that might actually occur. So this could be, for example, a high impedance earth fault, a low impedance earth fault, which would be applicable to the simple example that we have here, because basically we're looking at a point in the system where an earth fault could occur, and it could be a high impedance earth fault, or it could be a bolted earth fault. Or if we have, for example, some components in the circuit, we might have a charging circuit for a variable speed drive. We might have a power factor correction unit which has capacitors inside. These things can also be things that can be considered. Okay, so these are things like component failures where it goes open circuit, short circuit, or maybe a component value increases in value or decreases. So, for example, if you have a resistor in a VSD pre-charge circuit, that resistor might increase in value, and of course, by increasing in value, that might cause the variable speed drive to misbehave, and we want to be able to determine that particular fault location. Okay, and also we need to consider which particular phase the fault is actually occurring in as well. In other words, A phase, B phase, or C phase. And of course, that's in the simplest sense. Of course, you have something like a variable speed drive and you want to probe into that. You have to consider things like, faults on the DC bus, whether it's the positive side or negative side of the DC bus as well. So if we just look at our particular simple example, we've identified the two fault locations, fault 1 and fault 2. And we would have noticed also in describing those fault types, I've started giving them labels as well, basically saying, this is an earth fault and this is a qualifier for that earth fault. And in fact, this is a common theme that's sort of, I'm sort of showing here that labeling things becomes very important, especially when you start looking at lots of combinations of equipment. So here, for example, I've just labeled the faults F1 and F2. It might be that the fault locations could be labeled based upon the location in the plant, but either way, some sort of systematic way of doing it. This also becomes important in the actual physical implementation of the simulation model, which basically is something where a structure can be created of the system, but all the fault combinations that are then evaluated is an automatic process because you can't necessarily do them all manually because it would just take too long to do manually. So they're the two fault locations. Okay, so now we've got our modes and we've got our fault locations and types. So another thing, the third piece of the puzzle is looking at the symptoms. Okay, so we need to define what are the symptoms that we're going to be using as our input to finding a fault. Okay, so basically the things that we're going to be using are the mode of operation. So in this case, we have the four modes that I defined: O2S, sub, S2D, and DCB. Now, what we're going to look at now is what has tripped and the order of tripping. So here we have basically two devices that can be tripped. We have the incoming circuit breaker and we have the contactor and the DCB. Okay, and of course, which one trips in the trip order and what actually causes them to trip are important, and also the change in voltage and current. So just exploring what is tripped and the order of tripping. It's important to understand what the protection has actually tripped. So whilst the circuit breaker can open, it can actually open under various conditions. So in this case here, there could be backup earth leakage on the NER, which would trip an upstream circuit breaker, or it could be, for example, a overload protection that might trip. So that's important. And the location of the tripping, whether it's in the substation in this case, or whether it's in the DCB. Okay, and here I've labelled the trip locations as being sub and DCB. Okay, once again, we need to have some sort of way of labelling these things. So if you were to fully qualify what is tripped location, it would be the location that is tripped, whether it's a sub or a DCB, and what type it is. For example, earth fault. And in fact, in this simple example, we'll just consider an earth fault only in this case. So the last piece of the puzzle is the change in voltage and current. And in fact, this is very useful information and probably sometimes overlooked when debugging. Generally, when something trips, everybody goes to the point of this particular device trips. So let's look at everything downstream of it and start measuring motors, measuring cables, swapping out equipment until the plant starts operating. But the actual changes in voltage levels and or current, including the core balance, the earth leakage current, are all clues as to what actually might be going on. And for example, an earth leakage trip doesn't necessarily mean that there's actually an earth fault. It could actually mean there's some other imbalance in the system that's actually caused an earth fault. And the way we then quantify this is by basically saying, has the current or voltage gone up, gone down, stayed the same, or possibly gone to zero? Okay. So by defining these symptoms, we want to be very systematic and very precise about what we're doing, because we want to have a system where we can basically say, this is our symptoms, and then from that map that across to possible fault locations and fault types. Okay, so we'll see how that's done. Okay, So now if you were to then take that, how we actually go about locating the fault, which is the key thing for this presentation. So obviously, after we've done those three things that I described, we need to actually develop a model of the system, okay? And that model also includes being able to model the faults that we've identified as well, okay? And this particular model is not a trivial model. It can be actually a quite complicated model, especially if you have a medium-sized system with a number of with a DCB with a number of outlets and a number of loads. It can be quite complex. And then what we do is we want to then simulate the fault scenarios. Okay, so and this can take a very long time. So as an example, a medium system that has a variable speed drive might take in the order of 24 hours to run the simulation, and this is considering about 350 different fault scenarios. So you can sort of see how when you start looking at combinations of things failing, and with particular mode as well, there can actually be quite a lot. Of course, the whole thing's an automated process, so that's good. But of course, you need to basically develop that model first and then do the simulation. Okay, so from that simulation result, we can basically generate tables that map symptoms to probable fault locations. Okay, so in other words, when a simulation of a scenario is done, that's done under a certain condition. Okay, and the result of that simulation is going to be effectively those symptoms that I had on the previous slide as an input. Okay, so in other words, given that particular symptoms, the probable outcome is that particular fault scenario. Okay, now of course when this is done, we don't necessarily get a unique mapping. So in other words, you might find that as we do the scenarios, you might find that there might be a few scenarios that might map to the same set of symptoms. But what that's done is it's basically narrowed down, a large set of possible causes to say maybe, 2 or 3, which makes the debugging a lot more easier. Okay. And also as part of doing the information from the simulation, as well as generating these tables, which is the first port of call, generally also it's good to include the RMS voltage trends, which can then be compared with the SCADA trends. And in fact, the SCADA trends are what's actually being used to determine, for example, whether voltages go up or down when a fault occurs. Okay, and also the SCADA is also used to record what is actually tripped as well. So basically, the SCADA information is what's used as the input to the fault finding process. And also having waveforms as well of the actual signals can also be useful, especially for variable speed applications when you have high frequency content. So basically, the end result of all that is a fault finding manual and a worksheet that can actually be progressed through to actually find it. Okay, so generally, if you want to do that yourself, that's something you can do, but usually you get somebody else to do the above because it's actually a complex process. And of course, if somebody has a system in place that actually has a framework for that, it makes it a lot easier. So this is something that that ResTech has actually done, this sort of process. So how will we then use the worksheet? Well, basically the worksheet is then effectively a two-step process. First of all, you just record the symptom information. In other words, the mode of operation, the trip order, and the voltage and current change. And then step 2 is basically follow the procedure to find the fault, which is basically following the links in tables. And generally, to make it easier, 2 tables are used. The first table maps a particular mode of operation and trip order to a table which has then a set of voltage and current changes. And that second table, you then match the voltage and current changes to then look at the probable fault locations and fault types. And hopefully there'll only be one or a small number of combinations that map to what you see on the SCADA plot. And then you can check to see if the fault is at the probable location. Okay, and that means that you narrow into that very quickly without having to do anything other than just looking at the SCADA readings. Now, of course, if for some reason the fault isn't at that location, there are other things you can consider and this is also comes out of the simulation results to find probable fault locations, including things like nuisance tripping, where you might find that the changes in the voltage and current waveforms aren't as defined as would normally be, but nevertheless things actually trip. So just summarising that before I just go into a quick example. Basically, you want to model all possible fault scenarios, because generally if you don't model a particular fault scenario, you won't be able to reveal that fault. And faults are revealed basically during a transition between modes of operation. In other words, when something's closing, if you're closing under a fault, or whilst you're in a particular mode where the switching devices are in a fixed position during the onset of the fault. And the last point there is about being systematic with labelling, because generally if you look at a fault finding manual, there's a lot of labels used for mode operation, fault locations and types and symptoms, and it's nice to have a good system to make it easier to understand. Okay, so finally I'll just go through a quick example just to sort of show you the typical sort of waveforms that you might sort of find, and see how we'd actually apply that fault finding worksheet to find the fault, and hopefully see how straightforward it is. Whilst the example is quite trivial, and to find the fault would be normally trivial, it just shows the process. And if you think about how this could be applied to a more complex problem, you can sort of see the versatility of the process. So if we consider a fault, in this case we'll consider a high impedance earth fault in the DCB, so in fault location 2. So in this case it's an earth fault high impedance, EF-HI, and it's a fault location 2, and we're going to be basically in mode DCB. And mode DCB we've defined previously as being when the input circuit breaker is closed and the DCB contactor is closed. Okay, so the fault basically is at, in this case, the A phase, and that earth fault is basically connected to earth via a high impedance impedance. And in fact, in the simulation model, that's exactly how it would actually be. It would actually be simulating a resistor there of a particular value to simulate a high impedance earth fault. So if you think about what sort of trends and waveforms we might get, and here I've just pulled out some of the key ones rather than all of them. So here I've basically plotted waveforms for the substation and the DCB at those two locations that I had previously. So if I just go to the previous slide, where I've circled sub and DCB. Okay, so these are for the sub and DCB as a trend, and the sub and DCB as a waveform showing the actual 50 Hertz signal. Okay, so the signals are phase to earth voltage, which are shown as red, green, and blue, and also the core balance current, which is shown in orange. Okay. And I've also shown some other symbols on there, which makes it easier to sort of see what's actually going on. So the black triangle is are the points where we consider the signal changing from a before value or before the fault value to after the fault occurred. Okay. The red diamond is the actual point at which a fault is initiated. Okay, so you can see here where the red diamond is, there's a clear change in signals when the fault is initiated. In other words, when the high impedance earth fault is connected to the A phase. And the green diamond is showing the point in which the fault is cleared by a protection device. In other words, sensing that there's a fault, in this case an earth fault, and operating a switching device, in this case a contactor in the DCB. And the lines basically show an averaging period, because if we're going to be doing an RMS value, we have to actually average over a period of time. And in fact, these waveforms averaged over a very small period of time to give a nice, smooth, high-speed signal. And you can sort of see by looking at the period of the waveform the time value is actually quite small. Generally, with the SCADA system, we might be only sampling at 4, 2, or 1 times a second to get a result. So if we go look what the worksheet we do, we basically go through the steps we mentioned before. So first of all, look at the symptoms. Okay, we know we're in mode DCB. And the trip order is basically the DCB only trips. Okay, so I've shown there the green diamond showing the DCB tripping, and of course when the DCB trips, I think when I drew the if I just go back to the previous one, if you look here, when the DCB contactor trips, the DCB voltages are going to go to zero, and any sort of core balance measurements are also going to go to zero. So we see that there, once that trips, it goes to zero. And of course, in the substation, because the circuit breaker is still closed, the phase voltages go back to the normal levels, and the earth leakage current goes to zero. Okay, so we see that both the substation and DCB respond to the earth fault. However, once the earth fault is cleared at the DCB, the substation effectively goes back to normal. Okay, so we think about the signal change now. We see that the A phase goes down, and the B and C phase goes up, and also the earth leakage current goes up. And this happens for both the substation and the DCB. So this is the before the first black triangle and after the second black triangle. Okay, so then step 2 is follow procedure. So we basically locate the mode and trip order in the first table, and I haven't actually shown the first table. So basically the first table will be grouped in mode, and it will have the trip orders listed. So the idea is you go down the table, find the mode, and then you basically say, okay, is my trip order here? And let's assume that the trip order is actually there. It is possible that a particular fault scenario might not necessarily have a trip order found in that table, depending upon the fault scenarios that are modeled. But for the general part, it will be found. And if it's not, there are other things to look at. And then the second part is from that link from that table, it will refer to another table, which basically is a table for that particular mode and trip order that has combinations of signal change. And here I've basically shown a table with only 3 entries in it. This would actually have more things in there. But basically it shows that there's a set of different signal changes. And what we want to do is we want to match up what we had on the previous slide with one of those lines. And if we go down through that, we see that it actually matches up with that first line, which is saying that for that particular signal change, given a trip order of DCB tripping only, and we're in mode where both the input circuit breaker and the DCB contactor are closed, it's going to be a fault on the A phase, it's going to be a high impedance earth fault, and it's going to be at location 2. And then we would then check to see if the fault is actually located there. If it is, great. If it isn't, there are other things we can do to try and use the information to find where the fault might be. But once again, for the more common type of faults, it will actually find it. Okay. So just as a summary for that, I think you can agree that it's a very systematic method for locating faults. We just followed a very simple procedure, and we found the fault quite quickly without having to do anything other than effectively looking at what the SCADA information would actually give us. Now, of course, the SCADA would give us things like when devices are switching and what actually has tripped, which is good. However, the only thing that it's a little bit difficult sometimes, and may require some interpretation, is the voltage and current waveforms, which we might find, whilst we see a nice transient happening there, we might only find that we only have like 2 or 3 data points. But nevertheless, it still ends up being a way of matching up that to that. So finally, if I can just summarize or conclude with this slide here, just to sort of go through what I presented. Modeling fault scenarios does minimize asset time times, okay? And I hope I've demonstrated that by basically showing how easy it is to find a mapping between symptoms and expected fault locations. And this is all done just by looking up tables in a fault finding manual. One thing that I haven't done yet, or that we haven't done yet, that's also possible, is to actually automate the fault finding process. In other words, it would be possible to enter that symptom information and then basically get a result saying this is where it might be, rather than necessarily having a printed manual or a PDF file. And of course, there's even another layer on top of that, is that the SCADA system itself could actually be coded such that when a fault does occur or something trips, it could actually automatically say, I think there might be a fault in this location, rather than just telling you that this device is tripped. Also, whilst designing plant, you can actually make it easier to locate faults. What we saw is that knowing the mode operation does tell us, does isolate the fault location. So if you can design plant where there are actually maybe more switching devices than you would normally put, not necessarily going overboard, but if it can be designed such a way where you can have devices that segregate the equipment, the plant, that would actually be quite good. And also having additional measurements that basically also allows discrimination of faults, so that we basically learn more about what's actually going on. And the final point is, whilst having this fault finding manual and looking at all these fault scenarios is good, some sort of training is also relevant as well. In other words, being able to sort of go through and understand what these fault scenarios are and what to look out for, okay? So in other words, when a fault does occur and you are using this fault finding manual, it'd be nice to sort of go, okay, I've actually looked at this fault before, I understand what's going on, this is probably where the fault actually is. And if you think about airline pilots, this is something that they do very well. They basically train on simulators, and they train for finding faults that happen in the aircraft whilst it's operating. And of course, for them, it's an imperative that the aircraft keeps on operating, because they need to have it in a functional state. So whilst the motivation is slightly different, it's the same sort of scenario. So having some sort of training about using the information from the fault scenarios is also a good idea. So I hope that that has been informative and sort of shown you the benefits of modelling fault scenarios to minimise asset downtimes. And I'd welcome any questions.
Just got one question so far, but if anybody else does have a question, feel free to pop it in the questions box. So the first one was actually prompted at slide 11, which was, can you please explain bolted earth fault and the cases when it can occur?
Okay, so a bolted earth fault is basically an earth fault that is a low impedance earth fault, okay? So this can occur, for example, if a conductor was to make contact with another conductor, and in this case, with a bolted earth fault, it would be a face conductor making contact with a point which is actually at earth potential. So this could be something like a face conductor making contact with an enclosure, which is earthed, okay? So, and whilst in the mining environment, equipment is actually designed to minimise this from happening. It does happen, but of course, in an earth fault limited system, the actual current that flows is minimised as well. But that's what I mean by bolted. It effectively means a low impedance earth fault.
We've had a question. Which software can we use for fault modelling? Okay,
so basically any simulation package can be used. So the one that we use in ResTech for this particular application is LT Spice, but we also use PSIM for more complex systems. But basically, the framework can use any simulation package.
And this is just probably a question from me, Peter. So obviously, this is a real life project that you've worked on for a customer. So in terms of doing this work, how long would you say that it sort of took you to look at completing this manual and this piece of work for the customer?
Yes, well, it's actually taken a long time. So this particular project that was done, it basically was exploring about 350 fault scenarios. There was I think it was about 10 or 12 modes operation. So, and this actual simulation did take 24 hours to run and then get a result. Now, of course, what that doesn't include is actually setting up the actual simulation model in the first place, which actually takes a long time, because whilst the process is actually quite automatic once it's set up, and in fact we make use of scripts to do all this, we have to also verify that the results that we're getting make sense as well. And in fact, that's a common problem or limitation with all simulations is that whilst any simulation can give you a result, it always requires some interpretation to actually make sure that the result is actually making sense. And of course, when you have so many scenarios, it does take a lot of time to actually do that. Some of that can be automated, some of them not. But of course, in the first instance, because this is an initial project, it took a long time to set up the whole framework to actually do this. Yeah, so, and hence this is, I guess, if someone was to do it themselves, it will take a long time. But then again, if it's a smaller system, you know, it's not as difficult to do. But if you get anything that's anything that's mediumly complex, it's probably best to get help from somebody else. Yeah.
All right, thank you. So I guess on that note, if anybody does have any questions specifically around, you know, queries that they might have and a potential R&D project, or just wanted to pick Peter's brains, he's most certainly happy to receive an email or take a phone call because he may be able to assist or provide some advice. So we haven't had any more questions. What we might do is we might sign off on the webinar for today. Thank you everybody for coming. As I said, if you have questions or anything, feel free to get in touch with Peter. So have a great afternoon, everybody. Thank you very much. And we look forward to welcoming you to another webinar soon.
Thank you very much.